Welcome to the first video lecture for the MPP Calculus course. To those of you who are joining for the first time, these video lectures are designed to help you review the concepts from Math Camp and from elsewhere in life that you need for your Harris classes. We will focus our in-class time on actually practicing problem solving so that you come in having read and seen all of the material and so that you're not at home trying to do problems and getting stuck. So as you use these video lectures, there will be points when I come to example problems, and I encourage you to pause the video, try the example problem, and then start the video playing again. Each week there will be 2 or 3 different videos of lengths between 5 and 15 minutes that will walk you through the material for that week. All right, so with that said, the topic for this lecture is the conceptual foundations for derivatives. For this class, both because of time and because of how calculus tends to be used in your Harris classes, we are going to skip some of the focus on formally calculating limits that you saw in Math Camp, but we are going to talk in a conceptual way about how derivatives and limits are connected. So I'm going to start off with just a basic introduction to the idea of a derivative. The idea of a derivative comes from the idea of a rate of change. So if you have something like the graph that you see here, we might be interested, imagine that this is an indifference curve, for example, we might be interested in understanding how quickly the preferences are shifting from one to the other good at any particular place on the graph. Conceptually, what would tell us that is the tangent line to the graph at that point. And you can see that at 2 different points on this graph, the tangent lines that you draw will have dramatically different slopes. And what that's telling us is that depending on where in the indifference curve a person might be, their willingness to trade one type of good for the other is actually different. So we use derivatives in those ways, in a number of ways like that, throughout economics. On the face of it, it's not immediately clear how you would go about determining the tangent line to a graph at any particular point in time. If you have a circle, you know that the tangent line is perpendicular to any of the radii of the circle. But for curved lines, or for just about any functional form you're likely to see in economics, it's less of a natural jump to figure out how you might do it. Limits are useful conceptually because they help us conceive of how we would actually go about doing that. So what we do is we take, say, 2 different places on the curve and we draw a straight line between those 2 points on the curve. And you see that this line is not actually tangent to the graph. But what we could do is we could say that the slope of the graph between those 2 points is fairly well approximated by the slope of the straight line between the 2 points. And as you've done a million times in algebra, you can calculate the rise and the run as the change in y or over the change in x. So in this case, it would be a negative slope, and you would calculate some kind of a slope between those 2 points as the rise over the run. So if you imagine then moving them each in by just a little bit, you again can draw a line between the 2 points. It's not a tangent line, but it is probably going to do a better job at approximating the slope between those 2 points than the first line did. So you could calculate another approximate rate of change of the graph between those 2 points if you wanted to. And as you imagine, little by little, bringing this graph closer and closer in, you're basically talking about asking what happens as these 2 points get really, really close together. In fact, what happens as they become so close together that they are exactly equal to one another. And that will tell us the slope of the line, of the function at the green point here. So basically what we're saying is that we are taking the limit as the distance between the 2 points is getting closer and closer together. As we've written it, I've written it as delta y over delta x, but to translate it into the format you more frequently see, you simply realize that the graph has x on the x-axis and it has f of x on the y-axis. And so another way of putting this is that the slope is the change in the function f of x over the change in x. So now the limit that you're taking is really a limit as delta x approaches 0 of that slope f of x over x. Now this formulation matches pretty well what you've probably seen when you've seen the derivative form written formally. In a more formal sense, we write that the function f of x has a derivative, as indicated by this prime on the f, at point A that is equal to the limit as the value of x approaches the point A of f of x minus f of a over x minus a. And you can sort of see that this is the just another form of the limit that we've written here. So just to review conceptually what's going on here, we started with the definition of a slope, and then we asked what would happen to that definition as the distance between the 2 points on the graph shrunk so small that the points were on top of one another. And that's going to give us the derivative, or the slope of the tangent line at any particular place on a graph. Now, this particular formulation is defining the derivative for a particular point on the graph. Very often we're actually able to take a derivative that will give us a full functional expression for the derivative. So let me talk for a minute about what I mean by that. In the graph that we saw before of an indifference curve, you can see that the tangent line at different points clearly has different slopes. But in most of your economics classes, the functions you're going to see, you would be able to come up with a function that would describe the slope at every point as a function of the variable x. So one way to think about that is you are finding the derivative at some point x dot, for example, and you write it exactly the same way as x goes to x dot. X dot is purely made up notation here. But what this lets us do is it lets us think about it in generic terms that could apply to any point x. And for, like I said, for most of the functions you're likely to see in your classes, you're going to be able to come up with a full functional form, a full equation that will tell you the derivative not just at one point, but the derivative of the function at every point in the domain of the original function. The last conceptual piece we'll talk about this week is the distinction between continuity and differentiability. Formally, continuity says that if you take the limit of your function f of x as the value of your variable x approaches point A, it's going to be equal to the value of the function at A. So another way of thinking about that is that the function has no place where it suddenly does something different. So you're allowed to have functions that look like this. You're allowed to have great big points and curves and vertical and sideways lines. You're not allowed to have a function that does that, where there's a gap. You're not allowed to have step functions. Any place where the function is going along its merry way and then you have to basically pick up your pen. So at a gut level, a function is continuous if you can draw it without ever picking up your pen. The second you have to pick up your pen, it is not continuous at that point. Differentiability is a similar concept. It is related to continuity, but there are places where a function can be continuous but not differentiable. If a function is differentiable, it is continuous. So, for example, at the function that I drew just a moment ago, I had these sudden points. At those points where the function suddenly changed direction, it is not differentiable. It is differentiable everywhere else. These other two functions, where you have this jump discontinuity or a step discontinuity, they are also not differentiable at those points. I think it's a lot easier to see the concepts of continuity and differentiability through an example. So I'm going to go ahead and pull up a function real quick. So what we have here is the kind of function that math teachers create for the sake of having some examples to work with. In reality, you're only likely to see one of these problems in any given function. So here I have a crazy function. It's what's called a piecewise defined function, which means that it takes on different functional forms over different intervals. So some things to notice. You have x plus 1 over this region. At -2, the function is continuous, but it suddenly turns a corner. So while it is continuous at this point, at -2, the function is not differentiable. You have an asymptote for x minus 1 over x squared minus 1 at -1, where it goes to negative infinity from the left and to positive infinity from the right. At x equals 1, because of the denominator, you have a point discontinuity. And then where the function changes at x equals 2, you have a jump discontinuity where the function, you have to pick up your pencil and pull it up. So the function is defined. Notice that the function's domain here does not include the points -1 and 1, but it does include the point 2, even though the function is not continuous at that point. So you'll also notice that the function has a horizontal asymptote at y equals 3, but you can see that that's not affecting either the differentiability or the continuity of the function. So just to review, this point -2 is is continuous, but is not differentiable. This point -1 is neither differentiable nor continuous. This point x equals 1 is neither differentiable nor continuous. Sometimes we call this a point like this removable discontinuity because we could take the derivative of this function if we simply redefine the function at this point. So if we changed that piecewise definition to have a separate definition for when x equals 1 and set it equal to the correct value of the function right there, we would be okay. For the jump discontinuity, that would not work because as you approach from the left side versus as you approach from the right side, you would get different limits trying to take the derivative as you approached from the right here versus as you approach from the left. So at this point too, it is neither differentiable nor continuous. Now you might be asking at this point, why in the world is continuity and differentiability something that is important to be thinking about? The basic answer is that as you talk about defining, for example, people's preferences using a function, you very often want to take the first and sometimes want to take the second derivative of the function. And in order to do that, you need to know whether or not the function that you have created is continuous, is differentiable across its domain. Because if it's not, at minimum, you need to redefine the function in such a way that you're able to take its derivative. In fact, very often, the most natural functions we might imagine, we actually can't use because at some point we want to take a derivative and we're not able to. So conceptually, that's why it's useful to think about this in terms of for economics. All right, so that's a basic introduction to differentiation. There are 2 more lectures for this week. The first one is very quick. It's just a lecture about notation. And the second one is longer, but it's really probably the most important lecture of this entire class, having to do with how you actually go about taking derivatives without having to use the cumbersome machinery that you talked about in math camp based on calculating limits.